Hello, judges. Thank you for taking the time to review this. My name is Sunidhi and I'm a sophomore at Saratoga High.
I'm Shruti Vora and I'm a junior at Silver Creek High School.
Hi, and I'm Shreya, a junior at Silver Creek High School.
I'm Samanvi Bopana, and I'm a freshman at Saratoga High School.
And together we are Team Astra. We will describe our CubeSat design today. First, Shruti and Shreya will explain to you our requirements for the project that we have put together.
For our project, we're doing two different test cases. The first one is a little bit more realistic, while the second one is a bit more challenging. In our first test case, our goal is to orbit the CubeSat around the ground station with a fixed orientation at a radius of around 5 meters. We also want to take around 35 pictures in 2 minutes, which is roughly one picture every 3.5 seconds. We want our CubeSat to be able to identify 3 different pieces of plastic objects.
In our second test case, our goal is to orbit the CubeSat around the ground station in a turning orientation within a radius of 20 meters around the ground station, taking 35 pictures in 2 minutes to identify all 8 pieces of plastic. The difference between our two test cases is that the second test case has the objective of orbiting around a greater radius, identifying a higher number of plastics with a 100% detection rate, and having a constant turning orientation. The time bound, though, will remain the same of taking around 35 pictures in 2 minutes. We may adjust the number of pictures and time after initial prototyping.
The next thing we created was the concept of operations, which consists of 3 different modes: the pre-launch mode, active mode, and sleep mode. The pre-launch mode consists of a connection test, which tests that the satellite and ground is connected. Once our satellite passes the connection test, we move on to active mode, where it actively takes photos of plastics in the ocean. After the orbit is confirmed, we run our capture program readiness test, which makes sure the battery has enough charge and that the ADCS orientation is correct, such as the camera is facing the ocean, etc., to complete our mission. Once it passes that, the satellite takes an image and sends it to ground to check that the photo system is working. If, however, the satellite fails to take the image correctly, we have an on-satellite troubleshooting program which sends the ground whatever is wrong with the satellite. The ground then reprograms the satellite to make sure that the mission is able to work even with the errors. The capture program readiness test is run again, and it passes both stages. The next thing that happens is that it goes into a subsystem of the active mode, which is called camera mode. The satellite there takes multiple photos and filters out photos without any plastics in the ocean. Then it sends the photos with the coordinates of the photos to the ground, and which runs the capture program readiness test over and over. The reason we run this over and over is to make sure that the satellite is not on the dark side of the Earth. If it's on the dark side of the Earth, we are unable to take accurate photos of the satellite, of the plastics in the ocean, and the satellite is not able to recharge again. If this happens, then our satellite goes into sleep mode. Sleep mode is where the satellite runs a program readiness test at intervals to see when it is able to leave sleep mode, which keeps our satellite going in this active mode loop, which consists of our complete mission.
Here's the system level block diagram for our 1U CubeSat. In our diagram, we have 6 main subsystems, the first being structure, second power, third ADCS, fourth command and data handling, fifth communications, and sixth the camera. For the structure of our CubeSat, we have solar panels and an aluminum chassis. For our power, we're using solar panels connected to a SparkFun adapter and T-core batteries. As a part of the ADCS board, we have our IMU, which is an Adafruit 9 DOF containing the accelerometer, gyroscope, and the magnetometer. In our command and data handling system, we have a Broadcom microprocessor, and in our communication subsystem, we have our Bluetooth interface, being a Cypress chip.
Here are the subsystems which are active during the different modes of the previous concept of operations. During the pre-launch, we have the microprocessor and the Bluetooth interface as the C and DHS subsystem and the communication subsystem. And then we have, in active mode, we have the microprocessor, the ADCS, the power subsystem, the image recognition subsystem, and the camera subsystem, as well as the troubleshooting and sending subsystem. In the sleep mode, we have the microprocessor, ADCS subsystem, and the power subsystem, which are only active on intervals and do not work constantly.
Here is our current CAD model for the satellite. Let's start at the base, where we use the FlatSat as inspiration on how to attach the camera, IMU, and Raspberry Pi to the satellite. For the structure, we realized the holes were wrong in the angle brackets, so in the CAD, we created double holes to make sure it aligns. We then used the instructions to create the structure using the newly drilled angle brackets and the polycarbonate pre-cut panels. For the solar panel, we decided that leaving it at the opening opposite to the camera would give it the greatest amount of exposure to sunlight, and we decided to Velcro it on. Lastly, the power supply is in the center of the CubeSat, so it is easily accessible by all parts of the satellite. We used the given Bill of Materials sheet, or BOM, to create our own BOM for our CADed satellite. Our BOM includes the total and singular cost of each part in our satellite. We considered the quantity of the materials used as well. Our BOM excludes tools we used in making the satellite, such as screwdrivers and rulers, which were included in the provided BOM. For our mass budget, we used the weighing scale and measured each of the different parts of our satellite, and we used that quantity to create an estimated total weight of a satellite, which is grams. This weight was used to make sure our satellite matches the 1U form factor restrictions.
To calculate the power consumption, we divided the total mission's power usage into baseline power, power to take each picture, and the power to transfer an image. The baseline power includes the idle power and the power that is required for the ADCS to operate. We figured out that the total idle consumption was roughly 2.5 watt-hours, which is higher than the energy provided by the solar panels, which is roughly 1.96 watt-hours. So, we're assuming that the battery reserves around 1 watt-hour of energy. We also estimated that the power necessary to take an image and transmit an image would take around 15 milliwatts per image. We're also assuming that the time it would take to transmit one packet would be roughly 5 seconds. So in order to calculate the number of pictures we could take in our mission, we calculate the total time our CubeSat would be able to retain power by deducting the baseline power and the time for taking and transmitting images, which is 67 hours. We converted the total time into seconds and divided the number of seconds by 5 to find the total number of images. So through our calculations, we found that with our estimated power supply, we would be able to take around 48,000 pictures in around 67 hours. Our next action items are to study and reduce the idle power by turning off the camera until we need it and by possibly removing the Wi-Fi component. We also want to do a real-time experiment to get more accurate power measurements.
Next, for our software architecture, we have created a unique model that allows us to change the amount of power consumed by the ground station versus a satellite. As a team, we have decided that the most optimal use of our power would be to run a reduced precision neural network on the Raspberry Pi to check if any objects are present in the picture that the camera takes, rather than to send every image back to the ground station. Let me take a few minutes to explain the diagram present here. So first, the CubeSat makes sure that the ADCS system is turned on, calibrated, and ready to operate. After doing so, it reports back to the command control, which then alerts the image capture module to take a picture. Once the picture is taken, the command control is then alerted and it alerts the image recognition system to start processing the image. Once the image is processed and an object is detected in the picture, it reports that back to the command control, which then alerts the comm system. All of this has happened on the satellite itself. Once the comms on the satellite are alerted, the comms on the ground station are then alerted via a Bluetooth connection. The command control then gains this information and receives the image as a file. After doing so, the image recognition system on the ground station runs through the image and looks for any plastic. If plastic is detected, then the mission is working well. We hope to detect all pieces of plastic that we run through in our test cases.
For our link budget, on one side we have the estimated values which we calculated, and on the other side we have the experimental data we collected for receive power. We calculated the approximated receive power by taking into account the transmit power, which was approximately 10 milliwatt by Bluetooth spec, the free space path loss, the transmitter antenna gain 2 dBi, then transmitter loss 5 dB, receiver antenna gained 2 dBi, and the receiver lost 5 dB. In our research, we were able to find that the Wi-Fi Bluetooth chip on the Raspberry Pi via a connection through Bluetooth is able to recover the data as long as the receive power is between negative 89.5 to negative 95.5 dBm. Depending on the settings, we would still be able to recover our data. We noticed that our approximations made it in that range. We also found the experimental value for both our test flights to find the real-time receive power. For our first test flight, we found that without any barriers, we lost our signal at roughly 25 meters, which is well above our radius for the first test flight, which is 5 meters. To test our link budget for the second test flight, we added a lot of barriers like doors, and we found out that we lost the connection at around 10 meters.
Next, for our data budget, both the test cases will run for the same amount of time, taking a picture every 3.5 seconds. Though they're running for the same amount of time, the second, or more vigorous test case has a higher data budget than the first because of the amount of pictures that it transmits back to the ground station. While the first has an approximate budget of 273 kilobytes, the second has about 714 kilobytes. We've reduced the picture size from 720 by 1260 pixels to 240 by 240 because the data transfer to the ground station through the OBEX FTP would have taken too long, therefore failing the test case. As you can see on the right-hand side, I have written a test case without an image recognition system running on the CubeSat. This shows how much more data and in relation, power will be required to transmit all images to ground first, and then check for any important images in the file. This case, however, would not work because the data budget is far too large and all the images would not be transferred to the ground station in due time. Overall, I would say it's a fair estimate, although not exact because I've not conducted an experiment to find out the actual measurement for the data size. We plan to do this during the actual project execution.
For our integration and test plan, we plan to have 3 different parts, one for our CubeSat, the other for the ground station, and a final altogether. We start off by unit testing, making sure each individual unit is able to work by itself. We then subsystem test, where we start testing one system with another and seeing if they're able to work together. For instance, we check if image recognition and ADCS are working together by rotating the CubeSat and making sure it's only taking a picture when it's faced the right way and not taking a picture when it's faced the wrong way. Another example is when we check if our commands are being received to or from the CubeSat, which checks command and data handling and comms. For this next slide, we essentially have the same thing here, starting off with the unit testing of the 3 main subsystems, image recognition, comms, and command and data handling. And for step 2, again, the subsystem testing. For this part, an example of what we use is checking if an image is sent back and if the plastic is detected in it or not, which checks image recognition and comms. We then test it all together on our next slide by taking our CubeSat on a test orbit with a test object, where we start off by moving it and making sure that it's communicating that it's alive and not sending us any pictures. When it reaches the object, it should be taking a picture and sending it and the location where the object was found back to the ground station, where we confirm that the object is plastic and perform another test where we use an object that's not plastic and making sure that it doesn't recognize it as plastic. As you can see, we plan to devote substantial time for system integration and testing, as we expect this to be a complex and time-consuming process to get right. We hope you enjoyed our presentation and look forward to receiving your valuable feedback and working on our project next. Thank you.